The last two video segments that I'm going to be making on hybrid analysis. What you see here is an assembly like that, which is consisting of a solid cylinder in the middle, and then a plate, and then the beams which are holding this thing, and the beams are clamped at the ends. And this entire structure is given an acceleration of 10 g. For example, this whole thing can be sitting behind a truck, and the truck suddenly accelerates with a 10 g meter per second square acceleration. The clamp means that these beams are attached to the frame of the truck, for example. You should realize that this should not be done all with solid element. It has to be done a combination of beams, shells, and solids. Now, as the previous video segments on hybrid analysis showed, you can do this thing as an assembly, entirely as an assembly, or you can do it as a part. And I decided to do this thing as a part, and keep in mind that there is a plane of symmetry here. In other words, because of the nature of the acceleration, you cut it along the length of this thing, and that is your simplified model. So I'm going to create two video segments. One of them is going to be without plane of symmetry, and the second one is going to be with it. All right. So let's start with a part file, because I already told you that I was not going to do that with an assembly. Okay, so let's start here. All right, on a convenient plane, on this horizontal plane, I will sketch a circle. This is the circle which is representing that solid. Let me see for a second. It says radius 1, height of 2. Okay, so let's give it dimension. Diameter 2. Exit. And since we want to pad it, I'm going to go to part design. Height of 2. Okay. Then I'm going to go to wireframe and surface design, because I would like to make that the plate. So where is that? Mechanical design, wireframe and surface design. On a convenient plane, on that horizontal plane, I will sketch a centered, nice centered square or rectangle like that. And if I'm not mistaken, the length of this thing is 8 and the width of it is 4. So let's put some dimensions here. So this is going to be 8. Okay. And this side face is going to be, side edge is going to be 4. Okay, exit. And then we want to put a surface on this sketch. So right there, fill. Let me say okay. There we are. And we would now we have to make a decision on whether we want to make a hole here and then connect the surface of this cylinder with the edge of that hole, or we can just leave it like this and pretend that the bottom of the cylinder was glued or fastened or welded, surface welded to that surface. So I will go the second route. Okay, obviously these are different, and one should be careful depending on when these are done for real application. One should be taking into account the thickness of the shell here, and dimensions should not play. But what I assumed here is that the thickness of the shell can be, not that it can be ignored, you're going to be using it, but when it comes to these dimensions, these are nominal dimensions, so we just ignore the variation of the thickness. So thickness, half of the thickness up, half of the thickness down, but we are assuming that thickness is small compared to the overall dimension, and therefore we're going to ignore that. Okay, now the other thing is that we have to create these lines. Now, what was the length of this rod? I think these rods are 1 inch long, and it's circular in cross section, 1 inch long. Okay, so we need to do what we need to do. We have to create points, point or lines. So the method is point and direction. So there's the point. The direction is, let me see now, the direction in the x direction. Flip the direction and length of 1. And then repeat this thing on the other side. Okay. So this is the point. Direction is x. Flip the direction. The length is 1. And we have to do it on this side. So this is the point. Direction is x. Okay, that's good. And same thing here. This is the point. Direction is x. Alright. That's pretty much it. So why don't we save this thing. File, save management, save as, desktop, new folder, accelerating assembly. This is a single part. No symmetry used. No symmetry used. Okay. Alright, so let's put everything in there. Just a single part. Let's apply material to it. I think we said it was going to be made out of steel. That entire part is made out of steel. Okay, good. So now we're going to go to generative structure analysis. And immediately Katia is going to mesh that block. You see that? Change the rendering here. Right there, you can see that. Now we're going to mesh this thing with shell elements. So there we are. There is this. Make it 0.1. That's too small. Make it 0.2. Yeah, that's better because it's almost the same size as that guy. Alright, and put a thickness on it. Now I can't remember what the thickness of that shell was. Let's see now, the thickness of the shell. You gotta read these things carefully when it comes to doing the test. Thickness 0.1 inch. Okay, 0.1 inch. Very good. Now we're gonna have to mesh these beam elements with beam elements. These bar lines with beam elements. So let's see now, we're gonna mesh this. That's gonna be 5 elements. We're gonna mesh that. You can't do it simultaneously unless you join them, but we don't want to join them. And this. Okay, then the 1D property, circular, radius 0.05. Is that what it said? 0.02 actually. Okay. So let's change this into 0.02. Okay. So we're going to put it on this. And also on that. And on this edge, that line, and that line. Now, just to make sure that everything is working fine, let us actually, and the cross section should show up. I don't know why the cross section did not show up. Did I forget? Let me see for a second. No, they're here. So let me deactivate that. Let me see. Let me zoom in. Maybe so. Oh yeah, it's so small that you can't see it. Let me check for a second. What did I put as? Yeah, okay. Very small. Actually, these are too small. So we're gonna make that thing maybe 0.2 instead. Let me see how it looks like. right there. Okay, so how about making it 0.1? Look, it's garbage in, garbage out. If you put things that don't make sense, of course you're going to get results that don't make sense, which is fine. So this is going to be 0.1. Same thing with these guys. And with this last one. Okay, good. Now, save the analysis, file, save management. Analysis right here, save as in that folder. That's correct. Okay, so now we're going to apply the restraints. So this is clamped, so is that, and so is this, and so is this. And if you look close enough, the clamp sign is here, but because of the scale of these other dimensions, it doesn't show up very accurately. You can always make those things very precisely. You can always make those things big. Now we're going to create connection. Well, first of all, the beams are going to come into these edges as rigid connection. So let's start creating our connections. The first four are going to be for the beams. So first component is here. Second component, bring this thing into the show mode. Hide the beam. Hide this connection because otherwise you can't pick this node. Okay, good. Let's do this one now. Another connection. First component. Let's hide this guy. Ah, not that. Not the edge. Not the edge. Just the vertex. And for the second component, bring this thing in the front. Hide that guy. Hide the icon. Connection icon. So right there. Vertex and vertex. And repeat it on this side. Connection. Like this. First component is that vertex. Second component, bring this in the front. Hide that edge. Hide that white dot. Connection. That point, vertex and vertex. And the last one is over here. Let's hide this. First component is this vertex. Second component is the corner or the vertex of that plate. Okay. Hide this. Hide that. That vertex. And we say okay. Now these four connections are all rigid. Vertex to vertex always is rigid. So there is a distance connection property. This is rigid. This one is rigid. So is number 3. And so is number 4. Okay, so as far as the other connection is concerned, I told you that I'm going to create a connection between the face of the sheet and the bottom face of the this cylinder, and then make it a fastened connection. It means as if they were glued together. So another connection between that face. Second component, I'm going to hide this. I'm going to select the bottom of that. Okay, and this is this one, and we're going to make it fasten as if they were tied together with a glue or something. Okay, so save everything. Acceleration. So what we're going to do is we're going to apply an acceleration. Look under load. Here's the linear acceleration. You can see that. And the support is basically the entire part. The entire part, or you can select these things one by one, should be taking everything. So let me select the part here on the entire part body. Okay, There we are, but the direction of it is in the x direction. So x direction, not z, this is 0. In the x direction, 10g. 10 g is 98.2. 98, okay, something like that. 98. Oh, no. No, wait a minute now. Okay, 98 meter per second square, because my units are in inch per second square. So I type in 98 inches per second square. No, 98 meter per second square automatically gets converted to inch per second square. Okay? And we say, all right, save everything. Let's run it. I have a feeling that it's going to work. Yes, it did. So let me hide the tree. Look at the deformation. Doesn't surprise you. This is what happens. The direction of acceleration is like that. Yep. This makes sense. And you can look at displacement values. Change the rendering to material shading. So these are the displacement values, and you can animate it. I just realized something, and let me see now. I would have expected this to bend, to go lean in the other direction, because if you're accelerating, if this was behind a truck, and you were actually accelerating, I would say that this guy should probably lean the other way. Let's check our loads, see whether the direction of the acceleration is correct. Where is that load? Well, believe me, if this happens, it defies my intuition. I don't know. So if this was, let me see now. If it's accelerating, the body resists, so it goes the other way around. Oh, yes. You gotta be careful here, because if this is accelerating, the direction, because we are applying this thing as a static load, the direction must be reversed here. The direction must be reversed. Because let's hypothetically say that this actually was under the gravity loading, right? Under the gravity loading. So what you would do, the acceleration due to gravity is downward, all right? But you've got to be careful about this. If hypothetically this structure was sagging under its own weight, the acceleration that I would specify is going to be minus, in the direction z, minus, let's say, g, minus g's. And it's going to sag downward. Okay. Yeah. Be careful here. Oh, you know what? Yes, because we are applying this mass times acceleration as the resistance to motion. So it's got to go actually like this. And let's run it. I'm sure this time it's going to look okay. Yeah. Believe me, if this is sitting behind the truck and you accelerate the truck, accelerate that way, this bulky piece will actually go in this direction, in the opposite direction. Okay, the reason this is happening is that we are not really solving, we're bringing acceleration, but we are really using D'Alembert principle, where it says the force that is acting on the object is actually in the opposite direction. Okay, negative mg. You're solving the problem as a static. If your problem is solving a problem as static, the maximum acceleration should be considered as a negative mg. The acceleration should be in the direction. Okay. Now I'm going to stop this thing here because I would like to go ahead and use planes of symmetry to reduce this model. Okay. So let me